today's webinar on recycling PLA. I am the co-chair of the Sustainable Biomaterials Collaborative. We have four presenters today. We have Steve Davies from NatureWorks, that is a manufacturer of the PLA NGO resin, bioresin. We have Mike Centers of BioCor, who will be talking about buying and recycling PLA. We have Alain Descoins from Pellenc ST America, who's going to be giving an update on the cow recycle plan. We have Paul Fowler. We have Paul Fowler from the Wisconsin Institute for Sustainable Technology at the University of Wisconsin at Stevens Point. And he will be talking about PLA recovery and recycling pilot project on the University of Wisconsin. So let's get started. We're going to start with Steve Davies from NatureWorks. Steve leads communications and public affairs globally for NatureWorks, and Steve is going to be talking today on NGO from a cradle-to-cradle perspective, kind of broadly on the opportunities, the obstacles, and optimism. So Steve, you're on. Take it away.
Thank you, Brenda. And you were a little distorted just then, so if I'm coming across the same way or perhaps with an echo, I'd appreciate it if any listeners maybe ping Brenda or with a chat message, and we'll try and fix that. So unless you see any messages to the contrary, I'm going to continue. So again, Steve Davies with NatureWorks, and what I'm going to do in the next 15 minutes or so is discuss the recycled NatureWorks NGO PLA resins from three different perspectives, namely the opportunities, the obstacles, and then the path forward. Frankly, these three aspects are seldom heard all discussed in the same breath. And what I mean is that while the marketers out there love to wax on eloquently about the opportunities, many others will focus only on the issues and obstacles. You could say sort of really it's either a rave or rant often in terms of the conversation. Today I want to step past that approach, that mindset of either the cup being half full or the cup being half empty. And while acknowledging both, I want to focus on how we move forward, what's our approach, and why ultimately we are optimistic. Brenda, not seeing a slide advance. You have given me control of the deck, right? Slide's not advancing here. Brenda, don't seem to have control to move my slides forward. And meanwhile, I've had sort of a note from folks in our own building listening to this that the sound is extremely choppy. I don't know if you can do anything about that.
We passed the control on to you, Steve. You should be able to move forward now.
Okay, it does seem to be moving. Meanwhile, your vocal is pretty choppy, and apparently mine is too. Okay, but we will continue. So, going to my slide 2. Given the time constraints, I'm going to skip any introduction of who NatureWorks is and focus instead immediately on what's relevant for today's discussion on recycle, which is where our products are showing up in the consumer space, and so really what the post-consumer, post-use implications are. Today, as you can see on this slide, we're in 6 core markets, and what's often an eye-opener to many is the breadth and diversity of those markets. I reinforce this really because many equate recycle with plastics packaging, and our interests, obviously, in being in all these markets, our interests in recycle are far broader. We're interested in recycling every single one of these markets, ultimately, in the long term. Equally important to what the products are is, on my next slide, where they are landing geographically at the consumer level. Here you see shaded where we are sort of footprint, consumer products, and so post-consumer around the world. You can see that globally the products have very broad uptake, which means that for us it's important to be cognizant and aware of all relevant end-of-life opportunities for all applications in all geographies we sell into. What I'm getting at is that how a post-consumer package is treated in the US versus, say, how a post-consumer package is treated in Germany, for example, can be very different. And Brenda, don't seem to be advancing all the time here, so bear with me, folks. Okay, now advanced. So now all those products I've shown you, in all geographies, we supply with over 15 different grades of NGO PLA. With each and every one of those grades, we have a cradle-to-cradle philosophy. And what we're talking about is what's best laid out by Bill McDonough and Michael Braungart in a classic that I'm sure many in this webinar audience are well aware of. Our NGO resin grades are all cradle-to-cradle certified. And we particularly like McDonough and Braungart's approach because it is so holistic. Nature, in their scheme, nature doesn't see waste as waste. It sees it as a feedstock. And with this mindset, McDonough and Braungart categorize things as either technical or biological nutrients. We apply that same sort of thinking with NGO, and I want to show you what we mean. Broadly speaking, whenever my next slide advances, we see 5 options for avoiding the normal landfill fate of most plastics today. Some of these, of course, we have in common with petrol-based plastics, but 3 options in particular are unique to the polylactides. And I've shown those sort of with the grayed out boxes, what uniquely apply to the NGO PLA grades that we sell. Now, if we are focusing today on recycle, and with PLA there are 2 options for recycle. There's traditional mechanical recycle, what some call chemical recycle, and there's also what some call chemical recycle. What I've labeled here is feedstock recovery, and I want to explain exactly what we mean by that terminology. So on the next slide, I illustrate in simple terms what we mean by feedstock recovery. The NGO polylactides are polymers built from one green building block, lactic acid, and it's relatively simple with heat and water to recover that feedstock, the lactic acid, to just reverse the polymerization. I'll come back to this point because it's key in our scheme going forward. So that very quickly is some context on the opportunities that exist with NGO. What I want to do now is shift gears and talk about the obstacles. I'm not going to spend a lot of time on these, as our experience has been that they're front and center, front of mind for many in the market, and indeed that's likely why many of you are here listening. Simply put, the obstacles to recycling a unique plastic like PLA are really no different than those for any other plastic out there in a mixed stream. Things like polypropylene, polystyrene, or PET, for example. Each plastic is unique in terms of its physical properties and its characteristics, meaning that all plastics are contaminants in each other's recycle streams, and all typically must be separated if the recycle stream is to have high value. Excuse me. The obstacles can be summarized very simply as 1, identifying and separating another unique plastic. Secondly, gaining sufficient volume in the recycle stream that collecting that volume is of economic interest. And thirdly, having an end market for that material once collected. A 4th point I'd add is that we have to address all those obstacles while avoiding contamination of existing successful recycle streams that are out there. Now, these are common factors for all plastics, and indeed, these are the reasons that until very recently, the recycling success stories that we do see out there have largely been reserved to PET and HDPE and bottle applications. Thankfully, due to a lot of hard work from the recycling industry, that's beginning to change. So, given these obstacles, some very real and some frankly often more myth than real, why are we optimistic? Well, I want to talk now about our approach going forward, our approach to making recycle real. And simply put, it's a 3-fold approach. In a nutshell, our approach is to develop business, 1, by following a philosophy that some maybe from the regulatory space would call first do no harm. And what I mean by that is simply that we focus on selling our NGO PLA grades into consumer products where the potential for recycle stream contamination is minimal. Second, we've targeted markets for consumer products in which there simply isn't much recycle yet occurring today. Outside of bottles, that's a common situation and one in which the industry is really working hard to change. And it means that there's a good opportunity for us to work with this industry from the ground up to change, so that, in other words, when materials do begin to emerge from what is often an untapped number 3 through number 7 plastic stream, we want one of those materials to be PLA. Third point here is that we're working to develop scale, what some will refer to as a critical mass, to develop scale safely. That means growing it in a stream where there's maybe, unfortunately, little recycle occurring today, and where there are already numerous clear, transparent plastics that need to be properly sorted in order to be recycled. In those streams, in streams like that, PLA is no different than, say, polystyrene, PET, or polypropylene. They're all clear plastics. They're all contaminants to each other. They have to be sorted out to be of any value. So let's talk about the implications of this, because it's important to make something quite explicit here, that a fallout from this approach, if you will. This approach, the 3 bullets at the left, mean quite simply that NatureWorks has, for the past 3 or 4 years, severely constrained sales into certain applications. Specifically, here's an example, sales of our bottle-grade resin in the U.S. We've not taken on any new bottle customers in the U.S. in the past 4 years since we adopted this business development approach. And those that we do work with have had, frankly, several conditions of sale, simply put, some strings attached to the resin sales contract that basically amounts to what some would call a sort of voluntary EPR scheme. So now let me go on back to our approach. In addition to the threefold approach bulleted on the left, we are all the while simultaneously working to develop end markets for PLA recycle, characterize an NGO presence in the recycling system today, where it is, how much is there, and what its economic potential is, and then at the same time working with recyclers to address their sortation challenges. Brenda, this does seem to have froze again and is not advancing with me. So let's go to the next slide. Yep, and next slide again. Not sure. Okay. Now let's back up one. So, good. Everyone should be looking at a slide that says end market development. I'm going to spend my remaining 5 minutes then talking about each of these separately, each of these things, and starting with end market development. In developing end markets for recycled PLA, of course, there's 2 sources that can be considered, post-industrial and post-consumer. And PLA from either of these sources can in turn be recycled mechanically or chemically, so-called feedstock recovery. The sources are very complementary, meaning simply that each is exactly what the other isn't. Post-industrial scrap, for example, PLA scrap is readily available now and usually quite clean. Post-consumer PLA is a lot harder to come by, of course, and typically may not be so clean. So we think the sources are complementary, and similarly we believe that the recycle methods may end up being quite complementary. We often get asked at NatureWorks from folks, what method of PLA recycle, mechanical or chemical, do you think is going to win out in the long term? And we don't see it as an either or, frankly. At this extremely early stage, we're not picking winners. We think there's likely a place for both, depending on the characteristics of what it is that's being collected. Going to my next slide. I want to be very explicit about what I mean when I say that we think post-consumer and post-industrial sources are complementary. And simply put, trying to show that with this concept chart. If you look at a time scale and volume available as a function of time, simply put, in the short term, post-industrial scrap, the availability of that is the flywheel that's letting us start our end market development for our PLA. Post-industrial PLA scrap today is being sampled to a variety of end users, end converters, to develop our PLA applications. Over time, we expect these RPLA applications to act as derived demand for post-consumer PLA, giving what's really missing today, which is a reason for the recyclers to separate it. I'm not sure if you're advancing it, Brenda, but if you back me up on slide.
No, that's fine.
So we fully expect that, looks like the deck is getting ahead of me, but if you back up to slide 16 at some point, if you could do that, Brenda. Oh, sorry, to slide number 14. Good. Thank you. We expect the amount of post-industrial over time to drop, as shown by that green curve, simply because the converters interested in recovering their own in-house trim scrap, skeleton scrap, and so on will invest to recover it. And we expect the amount of post-consumer to grow based on demand derived from post-industrial PLA applications that we're working to develop right now. And now, advancing to my next slide, slide number 15. I'm going to show some examples of what's going on with feedstock recovery as an example of developing one particular end market. So let's start with post-industrial sources. What I find often here is frequently is that many in the market don't realize that at the post-industrial level, the feedstock recovery of PLA is already essentially a semi-routine operation. What we're talking about is NatureWorks' own off-grade NGO from our own Blair, Nebraska facility. Our normal practice is to hydrolyze such materials, off-spec materials, back to lactic acid. This isn't hypothetical. We've been doing it for about a decade now. We've hydrolyzed, turned back to lactic acid, about 25 million pounds of off-grade material since startup, recovered it and polymerized it back to virgin NGO grades. So the technology for this feedstock recovery is well demonstrated. The economics are well demonstrated. Now, of course, that is with a post-industrial supply. The hydrolysis process to regenerate lactic acid is product and format agnostic, meaning that we can put anything made out of NGO PLA or anyone else's future PLA for that matter back into a reactor, cook it with heat and water, and make lactic acid. The key question for us now is how do various post-consumer materials perform in this process? And we're beginning to look at that with some case studies. That's my next slide. I want to show you two quick data points here. I like these because of the product diversity they illustrate. The first is a one-off. It's the collection and feedstock recovery of the tens of thousands of yards of carpet, 100% NGO carpet that was used in the halls of the UN's Climate Change Conference in Copenhagen 2 years ago. After use, this temporary use trade show carpet that you see the delegates sitting on was rolled up and turned back into lactic acid quite successfully. The second example, going on my next slide, is what's really a commonplace in Belgium, Netherlands, really in the Benelux area. It's the use of things like NGO beer cups at the various music festivals, sports events, and the subsequent collection and hydrolysis of those back to lactic acid. So that is sort of a working model that not in day in, day out, but with many spring, summer, and fall music festivals in the Benelux area. Going now to my slide 18, what I want to do, having highlighted some end market development work we're doing, is to talk about what we're doing now in terms of my other 2 points, which is identifying and sorting NGO PLA at the MRF. I emphasized with an earlier slide the global nature of our sales and our consumer products focus, so it shouldn't really be a surprise to anyone here that we've got work going on in this area in numerous countries. I've captured them all here just to ensure the audience is aware, but in the interest of time, I'm going to talk in detail only about what's happening in the U.S. and in particular about recent work done by the APR. Other speakers today will touch on the other U.S. projects. So starting with slide 19, I've borrowed a couple of slides here from a presentation that the APR, the North American Recycling Industries Trade Association, of which we're a member, slides that they gave in a conference in Orlando 3 weeks ago because they capture it very well. The APR has long recognized that recycling plastics beyond number 1 and number 2 plastic bottles is an issue for a very broad group of stakeholders. Consumers want to recycle more plastics, and a wide variety of industries want more plastics recycled. So to address this, over the last year, the APR has completed a major project, if my slide would advance, what they call the National Bale Audit Program. Basically, this is a comprehensive assessment of potential supply routes to recyclable rigid plastics. It's funded by the APR Rigid Plastics Recycling Program members, of which, again, NatureWorks is a participant. And it provides an overview of where non-bottle rigid plastics recycling currently stands and where there's the potential to expand it. So, simply put, this involved, the bale audit involved collecting bales from numerous different representative MRFs and manually sorting them by both plastic type and packaging type. And I'm way oversimplifying this. It's a significant piece of work. It's captured in a 50-page summary report for members. Today, I want to highlight only one small piece of the work, and the next slide from Steve Alexander says it best. While that's coming up, okay, it now should be in front of you. Hang on. Okay, you're now looking at it. This is the one key summary slide and one of my last slides here before I wrap up that shows you what Executive Director of the APR, Steve Alexander, summarized for an industry conference 3 weeks ago. Basically, in the APR's own words, they didn't find a lot of PLA. Almost all of what they did find was in the flat thermoform category, not bottles, which sort of validates the earlier point and is the proof in the pudding behind the approach we've taken to stay out of the bottle stream. The West Coast household container bales had the highest percentage of PLA, and even that was a fairly low set of numbers. So, simply put, this work was key for us because and this involved manually breaking down bales and sorting them. Didn't have to involve getting into what sortation technique to use. But it confirmed that we stayed out of the streams we wanted to stay out of in terms of minimizing contamination, and that our job now is to grow critical mass in these rigid streams where essentially very little is being recycled nationally today, while we simultaneously develop end markets for those. So moving to my last slide, just summary. Time today doesn't, unfortunately, permit me to really get into what we're doing in all those other geographies I showed you with the same three-step approach. But what we're doing in the other geographies exactly complements what I've been able to highlight in the U.S. today. It's about achieving scale safely in the streams where we can not be a contaminant today, at the same time developing end markets. So,
unmuted.
I think my time is up here. I've highlighted some of the opportunities, acknowledged the various obstacles out there, and I hope, at least at a very high level, giving you a sense of our approach in addressing them. There isn't time to get into more outside the U.S. today, Brenda, but maybe a topic for another time. We like to say, all in all, there's a lot going on out there, but this is very early days. I can't emphasize that enough. So simply put, this is a start, and we look forward to sharing our progress with you going forward in this fast-changing arena.
Thank you, Steve. And this is Brenda Platt, the moderator today. I apologize for any technical difficulties. So presenters, if you're unable to advance your own slides, just please tell us next slide, and we will do it from here. So let's move on. And again, hold your questions to the end. Please, you can type your questions under the control panel under questions, and we'll start to go through those, and we will send them to the panelists. So our next speaker is Mike Centers of BioCor. He's going to be talking about buying and recycling PLA. Now, Mike is a 20-year recycling industry veteran. He's the founder of Titus Maintenance Installation Services, which installs and maintains materials recovery facilities in the western U.S. Mike is one of the founding members of BioCor, a company that was started in 2010 to actively recycle PLA from both post-consumer and post-industrial sources. So Mike, you're on. Welcome.
Thank you, Brenda. I appreciate that introduction. And I'll move right into these slides. I know we want to save some time for some questions. And you know, BioCor was founded about 2 years ago, and we're primarily going to talk to you about what's our business description and what have been the pilot projects over the last 24 months.
Muted.
One of the reasons we put BioCor together is, generally we need an economic reason in the recycling community to recycle PLA. We need to have incentives, either via movement as a cost avoidance from landfill or scrap value so that we can make money recycling PLA. And I noticed in here I used the 10. 10 is not the number for PLA. It is up in the ASTM standards looking for a resin identification code. It's one of the issues that Steve brought up, is identifying the resin compared to others. And obviously BioCor is interested in ensuring there is a number. It can be a 9, it can be a 10. It really doesn't matter to us. But here's what we basically do is we're looking for the post-consumer PLA, and we're looking for anything the recycling industry isn't currently recycling. And if you look at the recycling industry today, they focus on PET, HDPE, tin, aluminum, glass, and all the fibers. And they obviously get inundated with other products, whether they're new products with new packaging from new marketing or new products being driven by a consumer looking for alternatives to traditional plastics. And those kind of the dynamics that we're in today. And what we believe is that the materials used today for packaging may not necessarily be the materials 10, 5, or even 2 years from now. And we're seeing changes in the materials themselves. Just in reading alone, we've seen at least a 50% drop in news since 2005. And obviously that's due to the iPad. But packaging of all types and how we transmit data and information and products is changing. So we believe that if you look at what products in packaging are starting to emerge, a lot of it is a plant-based or renewable package, and we see that quite frequently, and seen it most recently with Pepsi's announcement to go to a renewable-based package, and Coke using the plant-based bottle. My next slide talks about why we like PLA from a recycling standpoint. For one reason, the economics of recycling PLA, Steve talked about, there's several ways to doing it. We can either convert it to a lactic acid and reuse it as industrial lactic acid, or reuse it to make more PLA. And we can convert it, regrind it, and sell it as an RPLA product. And at BioCor, we've done both. We've sent it to be used as under a 3/8-inch regrind, and it was made into a new product. It was a single-use product, but at least it was reused. And we've also sent it back for hydrolysis. We believe this product is already in our recycling infrastructure, but not in the quantities that are having an impact. But we're anticipating that could happen, so we're looking at ways to move those products out of the existing infrastructure. One of the pilot projects we're very much focused on right now is one going on with the Cal Recycle Group in Future 500. It's a bioplastics grant, and our next speaker, Alain, will discuss this in detail, but it talks a lot about how do we pull this material from a MRF. The other pilot projects that BioCor is focused on are closed-loop recycling. We've done several fairs, events, and stadiums, and we're looking at all types of PLA in this case, and whether it's clamshells, beer cups, or any other type that we can successfully hydrolysize or turn into RPLA. And then finally, post-industrial. Steve spoke about post-industrial. We're doing projects with yogurt cups and gift cards, as well as clear rigids. Quickly, I'm not going to take too much time, but the project in California was a joint project generated by a grant through Future 500. And the other project, which I think Alain will talk about, is all the stadiums and fairs. We've collected from the San Francisco Stadium water bottles, the Oakland A's Stadium, and Raiders Stadium relative to beer cups, and fairs and festivals from Chicago to LA and the Bay Area. A lot of these fairs and festivals and some of the smaller recyclers, we provide bags so that they can fill PLA with these bags. When you are not at a critical mass where you have continuous streams of volumes that you can create bales, there needs to be some assistance. And BioCor is like a bridge to get the small quantity PLA out and back into a recycling market. This is music festivals. This is also going on in Europe. Here's a little bit on what Steve was talking about, so I won't be redundant here. But I want to talk a little bit about these pilot projects that BioCor has been working on. In 2010, which was our first year, we converted about 170,000 pounds to lactic acid. Some of that was post-consumer. The majority was post-industrial. And we've converted about 40,000 pounds to RPLA. Last year, we did 60,000 pounds to lactic acid, and we have an additional 200,000 pounds in the queue. And our RPLA sales moved up fairly significantly to about 600,000 pounds. And one thing it's been a challenge for BioCor is that we may get a sample of PLA, and that sample, when we get the full load, it's not so much representative, and that's difficult when you're trying to process this material, and it's the same for any plastic. You have to have a degree of confidence in the quality level of the product, and that's one of our challenges. I also mentioned to you that on the chemical side, and Steve mentioned it too.
Welcome to GoToWebinar, Web Events Made Easy.
Kind of talking about what energy is going to look at pulling bioplastics, and specifically PLA out of the stream. We mentioned the Future 500 project. Cal Recycle and Future 500 partnered with two companies, Pellenc and Titus. And so if you take the Cal Recycle grant and industrial industry matching, you're looking at over $2 million. It hasn't been invested in determining how to collect PLA in the existing infrastructure. And also there's been some movement by Plarco in pulling material out of Europe. I think they've collected about 750 tons of PLA in the last year and a half. And some zero waste programs that have been established in either Boston, San Francisco, and several others. So there are energy going toward how do we move this product out of the stream. And in general, we're a for-profit company looking to be an end market for PLA. We'll buy both post-consumer, either from a closed-loop event or collected at MRFs or PET reclaimers. And we'll look at post-industrial. We've probably sampled about 65 separate products and are looking at buying those when it makes sense for either movement into an RPL or PL chemical lactic acid process. If you'd like to get a hold of me or learn anything more about BioCor and what we're doing, you can either visit our website at www.biocor.org, and I will be at the Plastics Recycling Conference in Atlanta, leaving here right at 1:30. And I have a booth there, so feel free to come to the booth, and you can follow up with me there as well. Thank you.
All right, thank you, Mike. So we're going to
Welcome to GoToWebinar, Web Events Made Easy.
It's going to give an update on the Cal Recycle grant looking at PLA and PLA recycling issues. So Alain, you are on, and if you need, we're going to give you controls to advance slides, but if it's not working, then we'll advance them here.
Thank you, Brenda. Thank you, everybody, also for listening to my presentation. So I'm going to cover
Muted.
the California-funded bioplastic project and where we are right now on this project. And to my presentation, and I realize the slide, I'm waiting for the slide. So, okay, we're here. To my presentation, I'm going also to give some answers to the first obstacle mentioned by Steve, the sortation of the PLA. Brenda, you might need to advance the slide for me. Thank you. So the sponsor of this project, as Mike mentioned, it's mainly Cal Recycle. The state of California participated up to $1.2 million on that project, and both Titus Company and Pellenc were added $800,000. The whole idea, it's a bioplastic project, so PLA is obviously part of this project, but we're also going to look at other bioplastics like PHAs and PHBs. And the whole idea of this project is to show that we can extract PLA in a very efficient way from the stream to provide a clean PLA stream on one side, and the other side also is to prove to a PET recycler or RCP recycler that they could receive from MRF streams without PLA in case PLA was a concern. So again, if you look on that side, the 5 primary goals were, number one, to show that there was an automatic way to extract the PLA through optical scanning. The second goal was to identify product made of PLA, but also other bioplastics. The third one was more related with quantifying the amount of PLA. The fourth one was to be able to demonstrate to MRF operators that there was a way for them to extract PLA, so they would not be scared about having to deal with the materials in the stream. And the last one, again, is to prove that we can do that in an automatic way, so that basically PLA is not disturbing any process currently in place at MRF. Brenda, if you could advance next slide. Okay. So brief overview of what an optical sorting machine is. It's basically a conveyor with a sensing head. So the sensing head will be able to analyze and define the materials on the sorting belt. Can anybody hear me? Okay. Then the sensing head will basically trigger nozzles. So through air nozzles, we're able to blow product in different directions. As you can see in this slide, for example, we can sort product in 3 different directions. You can see the 2, R, and 1. 1, for example, means that we will blow the product up. 2 means that we will blow the product down. And R means that the product will basically fall by gravity, by natural gravity. So with an optical machine, we can sort in 3 directions. 1 and 2 are called positively sorting, meaning that we trigger air to positively eject the materials. And 5 is the negative portion where the product just falls by gravity. Brenda, if you can move to the next slide. So in addition to the optical sorter, with Titus Maintenance, we designed this whole portable system that you can see on the slide. What you can see, this system is composed of 2 trailers. So the bottom trailers is composed of feeding hopper. So we feed the material on the upper left end of this drawing. Then the material is going into, I don't know if you can see my mouse, it's moving onto the screen to screen out some of the material that we don't want to see, like small pieces of papers. Then those materials will fall into a high-speed conveyor. So the idea of the conveyor is to increase the speed of the material to be able to separate them. Then we have the optical sorting here. The second trailer, so the one that's parallel to the first trailer, is there to provide utilities to the whole system. So we have a compressor and we have a generator. The idea of this grant also was to be able to demonstrate this unit, to use this unit at different sites and be completely independent from the utilities on site. So the idea is that we're completely autonomous with this system. Brenda, if you can move to the next slide. With this system, the typical PT bell coming from MRF. Number two, the typical HDPE bell. So those ones are the two main commodities marketed by MRF. Then we looked also at the mixed plastics, so the 3 to 7. The fourth test was with all the materials coming into the container line. So those ones will be plastics, but also metals. And finally, we look at the residuals. And for each of those different materials, type of bells, we ran 3 different tests.
Muted.
In addition to running all those tests at 12 MRFs throughout the states, so in order to have a lot of data. Brenda, if you can move to the next slide. Thank you. Here what you can see is pictures of those 2 trailers. So the one on the left shows you basically the feeding hopper for the materials. Then you can see the screens, and then toward the end of the picture, you might be able to see the optical sorting machine. The picture on the right shows you also the second trailer with the vacuum system to extract all the small fibers. Brenda, if you can move to the next slide. Those 3 pictures basically show portion of the optical sorting machine. So the top one on the left shows the containers falling onto the conveyor. The one on the right is towards the ejection of the optical sorting machine. What you can see on the optical sort on the picture on the right side, you can see those containers crossing rail flight. That's where the detection is made. The picture on the bottom shows you basically the size of the typical the optical sorting machine. Brenda, next slide. What you can see on this screen is how the optical sorting machine is recognizing different polymers. The left side, you can see rail flight. So we look at basically at the light reflected from the materials on the conveyor. So here, for example, you can see the top one is seen as by the machine as PLA versus the bottom one is seen as PET. So when we start an optical sorter, we basically characterize the machine, or we help the machine to recognize, identify each of the polymers. Then once the machine is in production mode, each polymer will be recognized, and then we can decide what we want to do with what we recognize, meaning that we can decide to eject up, down, or in the middle. Brenda, if you can move to the next slide. Here are the results from this test. So we are able basically to eject all the PLA we found with an efficiency of close to 100%, which proves that there is no difference in terms of the polymer is not the PLA is not a problem for optical sorting. It clearly recognizes that its own what we call signature, which means that we can distinguish the PLA from any other resin. Now we can again program the machine to either eject the PLA positively or keep it with the other product. Brenda, if you want to move to the next slide. So in terms of conclusion, what we find out in this test, since we had the 3-way sort, we use one of the positive sorting uniquely for PLA to be able to quantify the amount of PLA in the stream. We find very low results, so less than 0.1%. So we're in fact talking in parts per million. If I was looking at the contamination
Unmuted.
in TET or HDPE and so on, the contamination is in parts per million. It's not even in percent. So the first conclusion that in terms of quantity, the quantity is negligible today. If this became a concern, optical sorter can easily pull the PLA out. So there's absolutely no, I guess it's addressing the obstacle number one from Steve. There's absolutely no problem for technology to sort the PLA out. And the second conclusion that now we are applying this kind of concept to other bioplastics with Sky Recycle. So in the next couple of weeks, we're going to look at other type of bioplastics. Brenda, I'm done as far as I'm concerned.
Unmuted.
All right, thank you, Alain. So the last speaker is Paul Fowler, and he is the executive director of the Wisconsin Institute for Sustainable Technology, WIST, at the University of Wisconsin at Stevens Point. And there's a project funded by WIST. It's called the FRESH Project. It's a student-run research project, and it's looking at recycling PLA on campus at the food courts and the dining halls, and chemically recycling that back to lactic acid. So this is a closed venue pilot recycling project that Paul's going to talk about. So Paul, you are on, and again, if you have problems advancing your slides, let us know, and we'll do that from here. Is he unmuted? Okay. Hang on a second, Paul. You're muted, so we'll get you started again. There you go.
Muted.
Okay, thanks, Brenda. So the University of Wisconsin Stevens Point is essentially a community of 12,000 students and staff. Brenda said that the project was supported by WIST, but it's also funded by the Wisconsin State Energy Office. What we've done is take a look really at the post-consumer waste arising from dining services here on the campus. The project's called FRESH. It stands for the Focused Research Effort for Sustainable Habits. And about 3 years ago, the university's dining services switched out of styrofoam containers for both beverages and food into PLA-based food serviceware. The initial intent was that material would be source segregated and industrially composted. We've never actually achieved implementation of an industrial composting capability on campus yet, or up until the point of the implementation of the project, source segregation of those bioplastics. So what we set out to do was implement a campaign to collect both beverage containers, but also clamshell containers, which typically contain salads or burgers or sushi and so on. Look at the levels of contamination and also look at the level of success that we can have in source segregation, largely by implementation of a campaign to install waste collection bins, undertake a really significant marketing campaign across the campus, and then look at the so-called feedstock recovery or the chemical recycling of that post-consumer material, either after it had received a cold water rinse, or indeed just looking at feedstock recovery from the crude material, replete with lettuce leaves and Pepsi and Coke or whatever else may be in that waste. And ultimately, we want to look at the environmental sustainability and the economic feasibility of using and recycling these PLA products, with an idea, at least in the context of the Stevens Point campus, of trying to understand what is the best end-of-life management in terms of whether we should be thinking about industrial compostability, whether feedstock recovery is appropriate in this instance, or whether other alternatives such as anaerobic digestion might be the way to go. We really set out with an open mind, kind of focusing on chemical recycling as the focus of this project. So just to reflect on those objectives, the ultimate goal is to study the environmental sustainability and the economic feasibility. Short-term goal of the students, and as Brenda said, this is largely a student-led project, was to say, well, we've started to reap the benefits of using these renewable materials, but until the outset of this project, those materials were ending up in landfill. So the goal here is to divert as much of that post-consumer PLA on campus from landfill into other streams. And then we want to work with the broader Stevens Point area businesses that are already using PLA products to implement collection efforts, really with a view to addressing some of those earlier questions around the really small, relatively small volumes of material in the market so far. From the point of view of the science and research, we're very interested to evaluate the quality and the end uses of that post-consumer derived lactic acid, thinking there about non-food uses of this material. And then with life cycle assessment capability and expertise here on the campus to start to undertake some of those comparative life cycle assessment studies. The images that you see on this slide and on the previous slide reflect the marketing campaign that our students initiated across the campus. So we worked with a student in the creative arts to develop that logo across the top, and really the design of the posters and the marketing was all down to the students. We, as the Wisconsin Institute for Sustainable Technology, had no sort of editorial input into those posters, and we were really very impressed by the campaign and the way that it was implemented across the campus, across multiple venues, I should say. The major sort of closed loop site is what we call the University Centre, the dining court there. But the program has been rolled out to residence halls, to a convenience store, and to other eating places on the campus, takeaway cafes and so on. So whilst on the one hand the campus as a whole is a kind of a closed loop system, there's ample opportunities for material to disappear in terms of other waste streams. Okay. So the marketing and education piece was a major part of the project on the campus. So the initial effort was really to construct a timeline, recognizing that there's a really diverse number of stakeholders across the campus, recognizing that there's a lot of opportunity for material not to be collected by source segregation. So we wanted to be really clear about our messaging and promote the effort with a unified brand. We're fortunate in the fact that the majority of the PLA on campus is clear, transparent plastic, cold beverage containers, clamshells, sushi trays. We're also fortunate that none of the dining services outlets stock PET bottles. One of the features of the program is that bottled water is essentially banned from those outlets, or at least the students decided that they did not want bottled water. So there's a program which says, well, bring your own cups and so on for beverages, but we recognize that not everyone does that. So PLA containers are the other option. So all clear PLA cups, lids, sushi trays, clamshells can be dropped into specially designated waste bins. So part of the educational effort included a poster campaign, advertising on the collection bins, a Facebook and a Twitter campaign, a presence at the freshman orientation, and a dedicated website which can be accessed from that address which you see on the slide there. And then there's been a questionnaire and survey to understand people's habits, whether they're essentially using and disposing of the food serviceware in the place where they eat, or whether they're taking it back to their dorms and then looking for a route to dispose of that material back in their place of residence. So in terms of the logistics and the research for the project, what you see in the image there is some collected and bagged PLA serviceware in the university's materials and recovery center. The campus is very fortunate in having a materials and recovery center where the staff are employed by the university on all the campuses recycle it, whether it be aluminum cans, glass bottles, paper, cardboard, anything which enters one of the designated recycling bins, goes back to this materials recovery center right away for additional sorting, any additional segregation, where it's ultimately baled and then either sold on or goes to our nominated waste handler. So we set out to secure buy-in from a range of diverse campus entities: dining services, facilities management, the custodial staff, and the materials recovery center as well. And we see that really selling the merits of the project to those various stakeholders was a really important part of the initial setup. And so what we've essentially done is develop a how-to manual for other businesses who wish to start to implement collection or source segregation of material in their premises. So in terms of the research, we're looking to collect the weight data for the material recovered and then compare the amount of source segregated material that we recover against stock inventories. Because all our recycler comes into this building, we're able to understand the percentage rates of recovery versus material which is either inadvertently or accidentally ending up in the other recycling streams, whether it's into aluminum or the paper or the glass containers. We can really understand what the distribution of the mix is across those different recycling streams. The students as well are also undertaking a waste audit, so they're looking at everything that isn't recycled as well, the trash, to understand how much of the material is also ending up in the trash stream. So we're really starting to get a handle on the success of the marketing campaign, the success of the recovery, and so on. So we're really monitoring for PLA occurring in those other campus recycled streams. And then once we've collected all this material, whether we've rinsed it or whether we haven't rinsed it, we're then looking at evaluating feedstock recovery or chemical recycling. So essentially we're looking at the hydrolysis of that material, depolymerization of the polylactic acid back to lactic acid. And that's something that we're doing in collaboration with the Department of Chemistry here on the campus, looking to break down that PLA to the constituent lactic acid molecules, using those variations of those conditions that Steve Davies described, elevated temperature and pressure to essentially arrive at a concentrated solution of lactic acid. So some of the challenges, there you see one of our project students, Lizzie. She's sorting through some of the trash. That doesn't really reflect the quality of the PLA recycler that we've got, but that's everything else that's in the trash, and looking for elements of residual PLA that may have been thrown away there. So the challenges are, it's a dirty business, but the results that are coming out of this are, we think, really instructive in terms of how, from a source segregation point of view, an engaged population responds to the marketing efforts and so on. We also had a diversity of stakeholders on the university campus, so we had to achieve buy-in from all those constituents really to secure some success for the project. Another challenge was that in previous years the campus had been told that PLA serviceware was being composted, and so we're trying to make people aware, make the campus audience aware that there are a number of different end-of-life management options for bio-based plastics. Composting being one of them, but it's not the only route. And so starting a recycling effort required that different messaging, and I think we've been very successful in that campaign. But then there's also a bunch of other messages which are vying for the campus attention as well. So we see our advertising and marketing campaign. We also see that there are another plethora of issues that are vying for the campus's attention. And then there's these differing opinions, and we could talk for hours on end and still not reach a definitive position about what is the best end-of-life management option for bio-based plastics. What we're trying to achieve with this project is understanding what's the best end-of-life management option for those bio-based plastics in the context of the Stevens Point campus, and in the context of a chemical recycling facility being about 90 miles west from here in Eau Claire, Wisconsin. So starting to think in our life cycle assessment studies about the transportation footprint, about the end markets for recovered material, about whether there's a need to actually rinse and remove food residuals from the material, or whether the process is robust enough, and whether the specification of the resulting lactic acid is good enough for the end-use applications we have in mind. So the opportunities, we're really focusing on non-food end uses, and lactic acid has really well-known descaling properties, widely applied in household cleaning products. So we're starting to explore the opportunities of using this post-consumer recycled material, the feedstock recovery, the lactic acid, in household cleaning products. It's also a natural antibacterial agent in disinfecting products. So we see that there's a potential market and really nice product differentiation for brand owners who may be looking at the opportunities to use post-consumer lactic acid in some of their products. Also exploring the possibility of using the material as an anti-icer or a de-icer for airport runways. Currently, a lot of potassium acetate is used in those applications, and we see that there's a utility for lactic acid in those end uses, where we think maybe the specification could be a little lower than that required for the household cleaning products. And then the opportunity we see is really to use the life cycle assessment to assess the comparative impacts of those different end-of-life scenarios in the context of the University of Wisconsin Stevens Point and its close environs as well. As I mentioned at the start of the presentation, we're starting to talk to local businesses and institutions that are also using clear, transparent polylactic acid with a view to kind of pooling resources to increase the volumes and the quantities of materials that we can collect, and also to explore more fully the need or not to rinse those materials. So just a little bit about the team and the funding. You know that the hard work here, the organization and the project management was done by Juanita Kratz, a graduate student working in waste management here at the university, very ably assisted by Lizzie Lipinski, and it's Lizzie who gets her hands dirty sorting through both the PLA that we recover, but also the trash too. Amy Novak was responsible for some of the communications and marketing. Christine Kuhn from the point of view of the educational piece. Aaron Howard was the prime architect of the posters and the logo and the website, and then Dan Necker has produced a YouTube video. He's a student
Unmuted.
for the Pointer YouTube TV station, and I'll give you the web addresses for both the project website and a couple of YouTube videos which you may find of interest on the next slide. And funding for the project came from the Wisconsin State Energy Office. Special mention of John Baldus, who's the biomaterials specialist at the State Energy Office. We've been very grateful for the support he's provided the project. And we're looking at opportunities with the State Energy Office to partner with other of the University of Wisconsin system campuses to look at rolling out this program, but also to see about the possibility of anaerobic digestion as another end-of-life management for the bio-based plastic serviceware. The last slide, take a look at or jot down these tiny URL links to a couple of YouTube videos which sets out how the University of Wisconsin Stevens Point is telling a PLA story, and then also the piece on the Pointer news channel. And the final link there is to the project website. You'll find all our contact details there. If you need any further information, you'll find the email address and telephone numbers from that point. And that's my presentation, Brenda.
Thank you to all the presenters. We have a
Muted.
that have already come in, and I forgot to mention that if you still want to send a question, please do so. And if you want it directed to one of our presenters, that would be helpful if you indicate that. So while we're unmuting all the other panelists, I'll start with a question to you, Paul, which you actually probably in part answered. It was actually, are there life cycle assessments for the FRESH project effort already available? And I know you mentioned you'll be looking at those. And
they're not yet.
Okay, and then the other question is, if they're available, will they be available on the website, some of the websites you listed? So go ahead and tell us about any of the information.
Okay, so the life cycle assessments are a work in progress. We're making an investment in those life cycle assessments, and given the nature of the funding from the public sector, we will be making those LCAs available on the website in the fullness of time.
Okay. All righty, so let's, is everybody unmuted now? I think you are, so just so you know, Alain and Mike and Steve, you should be unmuted so we can hear you. So here's a general question. I think that, Paul, we'll start with you, but if anybody else wants to chime in, because I think it might apply to the mechanical recycling too. Does PLA or other bioplastic break down over time, and are there any issues of yield loss over time in the recycling process? So I'm wondering, Paul, for the mechanical recycling part, if that's anything that you've looked at, and then after Paul you've answered, Mike, we'll come to you.
We haven't looked at it from a mechanical recycling point of view. If I understand the question correctly, it's whether or not there's any breakdown prior to the recycling, or it's as a process of mechanically recycling. So I think prior to any mechanical recycling, I suspect that it's pretty stable.
Yeah, and then well, the other part that maybe you've looked into is the yield loss over time as part of the recycling process. You know, in chemical recycling, are you using a lot of material?
We're essentially using a closed reactor vessel to recover that material. So everything that goes into the vessel stays there. So we're not seeing any loss of yield as we produce lactic acid. We are doing a little bit of work to understand exactly how far the depolymerization goes, to understand that we've generated monomer, that we're not leaving behind any sort of die or tri oligomers of the depolymerized lactic acid. But in terms of yield loss, we're not seeing any loss of yield.
Mike Centers, do you want to add anything to this question of does PLA break down over time, and if there's any issues of yield loss through the recycling process?
None that we've experienced on the recycling process, but we don't have, you know, if you take an RPLA, let's call it 3/8" regrind from a product that's already made, and then you put it into another product, we don't have experience in taking that product and regrinding it and reusing it again and see if there's any change in properties. So I can't answer that part of it. But I know Steve has done some analysis on the hydrolysis side. I think he can answer that better than I can.
Okay. Steve, if you want to weigh in.
This is Steve. Yeah, this is Steve. 2 points. For the chemical recycle route, that is one of the key points that makes it very attractive, is there's not a loss in plastics properties, because you go back to the monomer, the green building block, and then you repolymerize virgin polymer. We do that, and there's no degradation in properties. You make prime virgin grades from it. That's for the chemical recycle route. For the mechanical recycle route, all plastics tend to degrade when they're repeatedly remelted, re-extruded, and reformed. That's a problem for all plastics in recycling. Why they have to be cleaned up, dried, and so on. Minimum physical property loss, I think, is the norm today with most plastics that are mechanically recycled, and it's what we've achieved with the developmental work we're doing with mechanically recycling PLA. Don't see that as an issue.
Okay.
I had the feeling from the question that somebody thought that the plastics might be composting along the way. I just want to make sure that folks understand that's not the issue. These products are shelf stable and will not compost until that property is switched on in an industrial compost facility.
Okay. And we do, just for the attendees, there were some questions on composting PLA, but we are not going to address those on this webinar. This webinar is really focusing on the recycling issues around PLA, both mechanically and chemically. One of the first questions we had is, and Steve, I think this one is probably best for you to at least to start off with, is what is the potential for recycled PLA to be on the market and included in products such as casing for printers?
We think it's excellent, and I say that because we're getting strong sampling requests now for our PLA. As I emphasize, most of what people are sampling today is what's available, which is post-industrial. It's not appropriate that I share who's doing what with it until they launch products, but believe me, people are experimenting with it because everybody likes to have recycled polymer plastics content in their products. There are already RPLA products on the market. Another question that came in was whether we could give an example of one, and for sure, an example that many folks may know is from ConAgra, who use they use PLA generally. They use our NGO grades to make tamper band, shrink wrap, and they use it to make this bundle wrap that might wrap, say, two products together when you buy a 2-for-1 type deal. ConAgra have been pretty vocal in their marketing to point out that that bundle wrap they use is our PLA. The question was specific to casings for printers. Those are typically compounded grades, and absolutely there's potential there. And the compounding community in general is very interested in looking at our PLA sources because they're very good at adjusting properties via compounding. So it's a good fit there.
Good. Steve, here's another question that came in specifically for you. And this relates to really that there's low recycling rates for a lot of conventional plastics, and the questioner, points out that like Coke's plant bottle can be, which is partly bio-based, can be recycled with conventional PET because it is PET, whereas recyclable PA applications, for yogurt cups add complication to existing recycling programs and complicate, capture rates and sorting and overall recycling. So the question he asks is, how can NatureWorks develop sufficient end markets when large associations and companies have failed to do so for conventional plastics? So recycling rates have grown, but they're still very low.
Yeah, a bunch of great points embedded in that question, and I think the questioner understood them well, but I want to make sure the wider audience does. Recycled, per the EPA, recycle rates for overall plastics are abysmally low. I think something like 7% of all plastics in North America are recycled. Most folks know much better the numbers for bottles, which are closer to 30% PET and HDPE. But if you look at plastics as a whole, all categories, it's like 7%. Why is that? Well, numerous reasons. One, until recently, the virgin plastics were simply much cheaper than the recycled, and so there was no business case that made economic sense to recycle. The other point was that there was nobody developing end markets until recently. And this kind of gets to the end question, which is, how can NatureWorks develop sufficient end markets when other large associations and companies have failed to do so for conventional plastics? There's a sea change that's occurred here in the last couple of years, and we've all lived it. That is, the sea change is oil now consistently over $100 a barrel, everything made from it more expensive, and suddenly the economics for the recycled material have completely changed. And what the recyclers have long wanted is now happening, that there's suddenly an interest in the materials they're processing. So that's the difference versus 10 years ago or even 4 or 5 years ago, that now the economics are favorable for the recycled materials. That's why the APR is working on that national bail audit to try and figure out how to get beyond bottles. We work with them on that so that we can take PLA out of that mixed stream. So that's the key difference, simple answer to the question. There was one other point in the question I just want to go back to, because the question basically emphasized that recyclable PLA applications like water bottles and yogurt cups add complications to existing recycle streams? They can, but I want to be crystal clear on this because it's one of the myths out there. Yes, there's no question that a clear, transparent Indio PLA bottle can contaminate a PET stream if there's sufficient quantity in there. I took pains, I think, to make the point that we've avoided that happening. So it isn't happening today, and the APR is, a firm voice in agreeing with us on that. Our strategy matches theirs. Yogurt cups, another story. The switch from polystyrene yogurt cups to Ingeo cups, driven first by Stonyfield and now international brands, dairy brands like Dannon. There's a desire for whatever reason to get away from polystyrene. Those folks have done their homework. No one better than Stonyfield in the U.S. to say that their existing yogurt cups are not being recycled today. The polystyrene cups were not being recycled. The Ingeo cup they switched to is also not yet being recycled. We're working hand in hand with them on that. But the point that Stonyfield makes pretty eloquently is that they have at least switched to a bio-based renewable resource with a lower carbon footprint. And they've addressed squarely the mythology that many consumers thought that their yogurt cups were being recycled. They were never being recycled in this country.
Okay, so here's a very technical question, perhaps, or a very specific one to be more accurate. Is the acrylic emulsion adhesive on the PLA labels we print an issue when it comes to recycling or composting of PLA? Anybody can address that question?
I think we're going to have to, speaking for myself, this is Steve, we're going to have to take that one offline and just check. I don't know. Never heard that as an issue in either compost or recycle.
Okay.
We can, you haven't said this, Brenda, but we can sure commit to revert in writing in whatever format you say is most appropriate on these questions that we don't get to address here.
Okay, yes.
Brenda, this is Paul. Some of the food containers that we're looking at recycling, the clamshells, have a sticky label on them designating what the food is inside. Well, I don't know whether or not the adhesive that holds those is an acrylic emulsion or not, but it's certainly one of the things we want to look at is that sort of level of contamination when it comes to chemical recycling. We haven't looked at it from or we're not planning to look at that from a compostability point of view, but from a chemical recycling point of view, it's one of our targets.
Okay, thanks, Paul. So here's a basic question, and there's probably quite a number of questions that in one way or another are asking essentially the same question. And Steve, I think you partly, and actually Mike, you kind of addressed this in your comments, but for the small amount of material, how can one justify the expense of optical sorting?
I can have a shot at that, Brenda, if you want.
Yes, please.
So one of the ways to address the issue of return on investment is to sort all the product that just, for example, PLA on one machine. So as I was mentioning on the machine we have in California, we can shoot in two different directions. So it might make sense for MRF to shoot, for example, PET, where we might recover a lot of it in one direction, and then PLA in a different direction. In that case, the PET will justify the cost of the machine for the PLA.
Okay.
That's an approach that's used, for example, it's very similar to the approach used by the Carton Recycling Council, where they needed to extract from streams aseptic cartons. They don't have volume. They face exactly the same challenge as PLA. They don't have the volume, so their idea is to eject aseptic cartons in one direction and then maybe use optical sorting to detect something else in a different direction. And then you can justify the cost of the optical sorting.
Any other panelists want to add to that response? Okay.
Mike.
So, Mike, go ahead.
I think Alain did a good job of answering that question. I think when you address the low critical mass products in the recycling stream, and you look at the way a lot of the products are being collected, which is single stream recycling, where a consumer makes the choice. Generally, a consumer believes all plastics are recyclable. And that is the core confusion more than anything else. And so once you collect them all, the optical sorters, as they come down in price and as they do a better job of keeping the high volume streams like PET and HDPE clean, are going to become more effective and more economical and more attractive. So I think the trend is toward more optical sorting at MRFs. Certainly is not ready for PLA, but the trend is a positive one.
So here's another stab at kind of addressing some of these challenges. This questioner asked, wouldn't limiting the usage of plastic resins in consumer products help with both the sorting issue, less types to sort, and also aid in the volumes of the resins that are collected?
Brenda, if you want, I can have a shot at that.
Yeah.
I used to work for Unilever, so I know pretty well the challenges faced by large packages. There's no way you can avoid plastics in consumer packaging. I mean, the other alternatives will be fibers, papers, and stuff like that, or metals. So in a cost, I would say for functional issues, there's no way you can avoid plastics. I'd like also to address the issue about plastic 1 to 7 at the same time, because for me it's linked to that. There is no general plastic resins that will be the solution for every problem. Every resin has its own properties, and instead of limiting the number of plastic, we're going to see an explosion of the number of resins in the market. The classification 1 to 7 is at the end of its life. It's not described in the market anymore. 1 to 6 were designed for consumer packaging good, but the 7, for example, category 7, we have all the engineered plastics as part of that. For example, all the plastics used for consumer electronics like ABS, PC, you will find those plastics in cars also. So for consumer goods, you don't have just the 1 to 6 anymore. You have a plethora of all the plastics. And these trends will only increase. There will be more and more very specific plastics. So to say that one particular plastic or resins will solve all the problem, it's foolish. I'm sorry to say that, but it's not going to happen.
Okay. There are challenges there with limiting consumer plastics in the market. So we have a couple of questions relating to optical sorters and the scanners. The first one is, can the optical sorters also separate PLA-coated paper products? And if not, what alternatives are there to recycle this type of product?
So the optical sorting, our technology is based on reflection. Other technology are based in transmission. In both cases, when you have a layer of a product, in order to detect it, you need to have this layer on both sides of the product, because you don't know in which direction the product will be presented to the optical head. Meaning, for example, if you have a bilayer product, you don't know if you are going to see the top layer or the bottom layer. So if it's a multi-layer composed of PLA, if the PLA layer is on the top, I will see it. If it's on the bottom, I will not see it. So that could be a challenge, yes.
And then and I would say that the alternatives to recycling this type of product, most of what I've seen, I'll just say, is really looking at PLA-coated paper going into the, for food service ware items and packaging, going into the composting end-of-life scenario. Okay, so the second question related to optical scanners was, how do the optical scanners treat bottles that have some PLA but mostly PET? And I don't know if actually there are any bottles, on the market that are mixtures of PLA and PET, but even if there aren't, I think that we're seeing a lot of blends of PLA with conventional plastic. So, this potentially could be a recycling issue in the future with how to address recycling of PLA when it's blended. So maybe Alain or Steve or Mike, you could address this kind of more generally.
Yeah, let me just address it from the point of view of the producer. This is Steve.
Yeah.
The question, if I've got the question right, how do optical scanners rate the bottles that have some PLA and mostly PET? I guess I'm confused. The question presupposes that there's blends out there. As folks selling, the only folks I'm aware of today, NatureWorks, selling a minimal amount of resin grade designed for injection stretchable molded bottles. there are no blends that we're aware of, certainly in volume. So it's been sort of an academic question, but maybe the experts on the phone could jump in on this one.
So Mike or Alain, do you want to add anything?
Alain, why don't you take this, because again, I think it has a lot to do with the detection technology. And
if there were blends, so the way we analyze components on an optical sorting machine is the light reflected back to our scanner. So if there was a blend of, I don't know, 10% PLA, 90% PET, if the light reflected back is very similar to the light reflected by regular 100% PET, I will not be able to distinguish it. That's just the blend. So my answer to that would be I will have to make some tests. It depends on the blend. It depends of. It seems to be a very theoretical question here. So if I had a mix of this potential PLA PET, I could answer. But right now I would say I don't know.
Okay. Let's see. I think I accidentally deleted a question. I'm sorry. So I think we've addressed a lot of questions. Have I missed any panelists that? So here's one I think here. I'm sorry. All right. I have seen a number of plastics which are only a certain percentage of plant-based material, like 30%. Is this really helpful when it comes to recycling the plastics, or does it cause more problem given Steve's comment about all plastics are contaminants and other plastic streams? Though we're not discussing composting, it seems like the mixed plant petroplastics would be a big challenge for composting for sure. I will. So Steve, I don't know if you want to start with
sure.
that.
I mean, sure, I'll jump in. This is Steve. It's really a question for the Coke or the Pepsis out there, but we know these folks well, and I think they share a frustration between them on the myths in the market on this one. When folks see a plastic like Coke's plant bottle, 30% PET, it's PET. The only difference is where it came from, bio-based, not petro-based. It's indistinguishably PET at the end of the day. It's not a contaminated PET stream, and it's why Coke has gone that route, sort of agreeing with our philosophy that bio-based content is critical to get low carbon footprint, and agreeing with us they don't want to interfere with their existing successful recycle stream. So those, I think what the question referred to is bottles that are, or articles that are marketed as 30% bio content. If they're one polymer, it's a non-issue in separation. If they are blends, then again, I can't, this is hard to generalize on, but our approach when we have sold our NGO resins into blends is to make sure they're going into blends that we're not going to be recycled anyway right now, unfortunately, and to make sure those blends are at least beginning to be bio-based and renewable content.
So we're almost at the end of the webinar. I'm going to just close with one other question that anybody can jump in. And I think, you know, we've heard some challenges with, well, the good news is that there's not much PLA showing up in the bale to be a contaminant, but we, you know, in developing a path forward for recycling PLA, there's its ability to be recycled. We know there are cost issues and challenges. We heard from Paul about closed venue collection systems for chemically recycling. So my question is, in terms of moving forward in the short term, do you see that one of the opportunities is to do more closed venue recycling along the lines of what WIST is supporting out in Wisconsin? So Mike, shall we start with you?
I'll go ahead and address that. You know, when it comes to recycling PLA, BioCor is interested in purchasing any collected PLA. And economically, it's much easier and it's economically more effective to collect in a closed loop environment. It's easier to concentrate the material, it's easier to train the staff on separation, and it works much better. It gets more difficult when you're dealing with the regular recycling market, primarily due to the critical mass issues difference between what's in the stream today and where PLA is today. So generally, we're pretty comfortable with end-of-life closed-loop collection systems, and that's where we've been successful with on the post-consumer side with BioCor.
Thank you. If anybody wants to add to that, please do. If not, what I'd like to do is close this webinar. Thank all of our panelists for their time today. If there's any questions that we feel we did not address that you sent in, we'll send them to the panelists and try to get responses out to all of the attendees. And those of you who are still on, thank you very much for your participation. So thank you all.
Brenda, if I can make a last comment for the people who would like to follow the development of the bioplastic project. Our next step is to look at the material received by PET reclaimers, because they have to tell us basically how much of a problem PLA is, because right now we're looking at, again, parts per million of PLA. And so that might address a lot of issues, because it might, part per million might not be considered a problem by PET recyclers. So I will assume in a couple of weeks we'll have enough data to see what PET recyclers are actually receiving at their plants.
Okay, and Alain, if you make that available through the Sustainable Biomaterials Collaborative, we can get out any information or updates to all the attendees who registered.
Excellent. Okay.
Okay. All right. Thank you all. Have a good day.
Thank you, Brenda.
Thank you.
Bye.
The organizer has ended the session.